Welcome to the RE4AFAGRi online trainings. The RE project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement 963530. This online lecture will introduce the RE4AFAGRi dashboards and present some concrete cases for their use. As already seen in previous lectures, the RE4AFAGRi modeling platform is a multi-model framework to analyze deficits, requirements, and optimal solutions for integrated land, water, agriculture, energy development nexus interlinkages with a specific focus on developing countries. In particular, as part of the RE4AFAGRi project, for models that represent land, water, crop, food, energy requirements, and dynamics, have been calibrated and soft-linked within this RE4AFAGRi platform. As seen in the diagram over here, the four models are water crop, MLED, onset, and nest, and they interact in multiple ways among each other by soft-linking their outputs and inputs in terms of requirements, needs, constraints, technological barriers, and technological enables and optimal solutions, to culminate with a general systemic solutions that is aware of all these different parts of the puzzle. In this context, the RE4AFAGRi visualization dashboards, which are available online for use on the RE4AFAGRi.Africa website, represent a powerful decision support tool based on interactive dashboards. These dashboards have been developed using the outputs of the modeling platform that was just introduced before, and they have the specific aim of supporting private infrastructure development in their site selection for maximizing financial sustainability and their development impact. Moreover, they also aim at supporting policymaking through assessment of subnational gaps and needs, in order for tailored measures and investments to be targeted. Finally, these dashboards are also enriched with direct access to download the raw output data for further scientific analysis. Once accessing the RE4AFAGRi.Africa website, one can navigate to the dashboards webpage, where a number of countries are already available to be used. As you can see, there has been focus on 5 country studies as part of our RE4AFAGRi project: Zambia, Rwanda, Nigeria, Kenya, and Zimbabwe. However, work is being carried out and will be extensively carried out with the collaboration of the broader scientific community to expand the framework and the platform onto other countries. Once entering a country's page, then it's possible to visualize the different dimensions that have been analyzed through the modeling work in each country. And for the example of Zambia, which is the most comprehensive one of those available so far, it is possible to explore dynamics such as cropland and water requirements, as well as energy and electricity demand, and crop processing throughput and demand for cold storage and processing as well as yield and yield growth potential in relation to irrigation and electricity access planning, that is to say, cost optimal identification of energy access solutions. And finally, it's also possible to derive some multi-sectoral insights that come from the message nest model. Once entering a dashboards web page, it is then possible, for instance, here we are showing the irrigation requirements and agricultural dashboards. It's possible to visualize different subnational units of a country and the distribution of a desired indicator of choice of the user onto a map that represents in shade of colors and also with numerical values the corresponding indicator value. Selectors allow to select different dimensions, such as the scenario, the year in question, which crop to explore, and different assumptions on what are the estimates that the user would like to visualize. Of course, these selectors are very much dependent on the dashboard in question. For instance, here we are in the agriculture and cropland dashboard, so we can choose between different irrigation types, crops, and as well as proximity of cropland to the settlement. However, in other dashboards, such as the technological ones, then it's possible to select between different technologies. However, some indicators, such as the scenario and the year, are consistent among all dashboards as they are homogeneously modeled across models. To take a closer look inside the dashboards, I will access the RE4AFAGRi.Africa website and present you a brief overview of its functioning. So, as you can see from my browser window, this is the landing page, the homepage of the RE4AFAGRi.Africa website, which is rich in materials. Contains, for instance, a user guide about the functioning and results of the dashboards, as well as a web page that better illustrates the underlying assumptions and dynamics in each of the scenarios, which then is found in the dashboards. The dashboard page itself, which can also be accessed by a main click here in the center of the website, and also much more material that will be then explored in the following set of videos as part of these online trainings, such as the business models and code, data, and documentation for the RE4AFAGRi modeling platforms. But here, if we enter the dashboards, as shown before, we land onto a country selection webpage where we can orient each other and choose one country. So what if we select Rwanda, for instance? So in the case of Rwanda, as mentioned, not all dimensions have yet been modeled. For instance, you can see that electricity access planning and multi-sectoral insights are grayed out, meaning that modeling work onto this dimension for this country still has to be carried out. However, other dimensions are accessible. So if we enter, for instance, the crop processing dashboard, we can then enter and wait for a few seconds for the web page to load until we are exposed to the visualization that we desired. There you go. This is the crop processing dashboard for Rwanda, where we have an overview. So here we're, for instance, visualizing in year 2020, that is to say the baseline year in the modeling work, which is more or less equivalent to the current situation. For maize, the yearly total crop throughput, that is to say the agricultural output that the models estimate to be suitable for local crop processing within access to markets, as well as corresponding electricity requirements for processing and storage. And this is interesting because we can have skim through the different regions of a country and identify which region emerge as the dominant regions. For instance, looking at maize throughput today, looks like that the Gankiki region, which I can also identify here below from the box, seems to be the one with the highest crop throughput. As you say, the unit is 1,000 tons. So we can see about 0.66 tons. 1,000 tons of maize are suitable for local processing in the Gankiki region, according to the model estimates. If I change an assumption, for instance, if I go into the future, if I go into 2050, let's say, we can see what the models project these indicators to evolve. So we can see that the situation changes in the sense that even if Gankiki is still deemed, even in the future, projected to be the dominant region in Rwanda for maize throughput feasibility, however, the amount of throughput strongly grows to 2,400 tons as a result of the increase in crop yields that the agricultural models estimate for the baseline scenario. Once again, if we switch scenario and we seek to look into the ambitious development scenario, for instance, where more ambitious goals of food security and crop production are assessed, then okay, let's look at the map. The Gankiki region still seems to be the dominant. However, a striking 18,000 tons of maize throughput are estimated to potentially occur in the region as a result of the ambitious scenario presenting a setting of nutrition security as a policy goal that needs to be met domestically, and as a result, a strong increase in the maize production, which of course will also be mirrored in the irrigation requirements and yield growth potential dashboards that are also available on this website. Let's now proceed introducing some use cases of these dashboards through an hands-on session that demonstrates how the dashboards can support different type of decision by providing information and analytics that might be useful for different type of decision makers in their investment and policy decisions. Our first use case concerns Anne, who here is our president of the Smallholder Farmers Association of Zambia. In particular, Anne wishes to identify which regions in her country have the strongest need and potential for expanding maize irrigation. To achieve these goals, she is in particularly asking herself in which region is it most effective and potentially profitable and also impactful to invest in maize irrigation expansion. And in particularly and relatedly, how much water and pumping energy is required in those regions to achieve these expansions. So to address these questions, we will use different dashboards, and in particular the water and agriculture one, the energy demand one, and the crop yield one, to assess and try to answer these questions. Here in the picture, you can see an example of a drip irrigated maize field. First of all, starting from the agriculture and irrigation dashboards, it's interesting to enter dashboards and decide which horizon year Anne has in mind. So in the screenshot here, you can see we are taking first a look at the baseline scenario, but we're looking ahead of about 15-20 years. We are going to 2040, and also specifically we are beginning by looking at irrigation requirements that the model estimate to occur close to the settlement. That is to say, cropland that is not very much distant from a community where people live, where farmers and the rural community live, which might be more suitable to be connected to centralized water infrastructure and electricity generation options, as opposed to cropland that is much farther than this one to the community, to the settlement. So looking at this, it's interesting because we can already get a sense of which areas of Zambia seem to be prevalent in terms of maize demand for irrigation to close the yield gap that is pursued in the baseline scenario for year 2030 for cropland that is close to the settlement. You can see a number of regions in the central part and in the eastern part of Zambia that seem to be the largest requiring in terms of water for maize irrigation. On the side, we can also compare on the left dashboard, in the agricultural land dashboard, the current distribution of maize rain-fed cropland, which partially, of course, mirror the regions which seem to have a high demand for irrigation water. We can also try to assess the same piece of information, but for cropland that is estimated to be remote from settlement, as I was anticipating before. That is to say that might be more suitable to rely on standalone water infrastructure and energy supply, as it might be too far to be connected to centralized options, and therefore has completely different both technological requirements and technical challenges and economic costs as well. So it presents also, the result presents a different outlook with other regions that emerge as more significant in terms of demand for irrigation water as a result of this different consideration of which cropland are we looking at, which is crucial for both public decisions and private investment. We can then proceed and take a look at the electricity demand dashboards, where also we can find two types of irrigation sectors. We can find an irrigation sector and an irrigation sector off-grid. That is to say, that mirrors the demand for water pumping that is remote from cropland, from settlements. And also here we can, of course, select the most suitable selectors options in terms of horizon here, scenarios, etc., to observe which regions are estimated to have the highest demand for water pumping and distribution onto the field for achieving irrigation goals that are defined by each scenario. It's also interesting to reason in comparative terms, so in terms of comparing the different scenarios to assess how big of a difference there exists between these different levels of ambition in terms of development goals to be achieved. And also it's important for planning purposes to check the seasonality of the demand, and the vast majority of the RE4AFAGRi dashboards present information disaggregated at a monthly level, besides the yearly total, to provide this type of seasonal evolution information. Looking at the crop yield and crop yield growth potential, we can also evaluate regions where rainfed maize is expected to have the strongest yield growth response if irrigation is performed in currently rain-fed cropland. It's rather interesting. Of course, this is a function of several factors such as local climate, terrain conditions, and so forth. And it's quite interesting because it shows that there are some regions which have today substantially higher yields in terms of tons per hectare per year of production. However, regions that are expected to benefit the most from irrigation are not necessarily the same one. So there are certain regions that seem to have a comparative advantage in terms of where it's better and most impactful to invest in order to improve maize yields in areas that today are rain-fed. So altogether, from this first example, we can try to answer the question depending on our goals, on our ambition, on our level of target, such as the example of Anne here in this first case, of whether small-scale, highly effective projects or large-scale irrigation schemes are more suitable to target a certain crop, a certain target. So it's very interesting to check, for instance, the area side by side with the yield growth potential, and also try to get a sense of what could be the total yield growth in each region, besides the yield per hectare, to get a sense also of the overall total size of production growth that might be achieved with irrigation, as well as what water and energy volumes are required to meet specific goals, and therefore what this implies in terms of resources management and infrastructure investment. Also keeping an eye of what this might entail for water energy system planning. Moving to a second use case, we have here, for instance, Joseph, who is the CEO of a Zambian mini-grid company that wishes to identify which regions have the strongest potential to build productive energy uses focused mini grids. So standalone grids that are not connected to central grid, but provide sufficient power to support households as well as different type of productive activities. So to answer these questions, we will specifically inquire into which are the regions with the highest projected share of mini-grid PV as a cost-effective electrification options, as well as which regions seem to have the highest level of potential productive energy demand to support the electrification private investments and customers' affordability to pay, as productive demand is a crucial component of the economic feasibility of electrification expansion, in particular in remote decentralized communities. Here, for instance, in the picture, you can see the example of a beautiful rural solar PV mini-grid. So to address this question, we will seek to use the energy demand and energy supply dashboards and output data. So first of all, accessing the energy supply dashboards, we can identify, based on the onset model results, which regions seem to have the highest projected share, so the number of new electricity access connections in a given scenario, in a given horizon year, that are best or cost optimally achieved with mini-grid PV, which is the technology of focus of Joseph, who is the mini-grid company CEO of a mini-grid that focuses on PV mini-grids. And on the side, we can also observe in terms of cumulative capacity requirements in each region, how big of the power generating investment should be to target, let's say, the community, the whole community that lives in a given region, to get a sense of where the largest markets are. In parallel, of course, it's crucial to observe also the demand related in these sectors. And as said, Joseph would like to ensure that the regions that he selects for investing are regions which have a significant non-farm SME, that is to say, productive uses that are not related to agriculture, available, and there is an important potential for this demand, as this demand is a really strong enabler of the economic feasibility and of the use of energy in the community. So here we are looking at the non-farm SME energy demand in 2030 for the baseline scenario at a yearly level. And of course, together with the previous dashboards and comparing the numbers and observing on the maps side by side, it's clearly possible to assess which regions are both promising in terms of PV potential, mini-grid PV potential, and also in terms of the size of the mini-grid of the non-farm SME demand. Interestingly, when the colors of the maps are not yet sufficiently clear to get an understanding of which regions emerge as the dominant one, it's also possible to overlay with the mouse and also use the box ribbon to see visually a pop-up which will display the underlying numerical value. For instance, in this dashboard, as you can see from the title, the unit is gigawatt hour per year. So just overlaying the mouse to a given region or to a given ribbon, we will see how many gigawatts per year are estimated for non-farm SMEs in 2030 for the business scenario. So altogether, this type of analysis allows to get a first-order overview to identify provinces and areas with the largest estimated potential for mini-grid PV and productive demand. However, a planner might be also interested in then looking at what's happening within some of this region that she or he identified as the best regions with the most promising region. And in this sense, it will be possible, as we will see at the end of this lecture, to download cluster data, that is to say, data that are very much disaggregated, the specific settlements that exist within of each region that is shown in the dashboards to really look at a very local scale and analyze more in detail which are the most promising communities and districts at a local scale for this type of investment. Perhaps also keeping an eye on their current electrification status, their size in terms of population, and also their socioeconomic status. A third use case that we would like to bring in this online training using the RE4AFAGri dashboards concerns, again, Anne, who we already met in the first example, the president of the Smallholder Farmer Association of Zambia. But in this case, she wishes to identify which regions have the strongest potential to promote pay-as-you-go solar mills, as the one you can see in the picture to provide an example. That is to say, milling machines that can be powered by solar, that is to say, off-grid. To answer this general question, we can disaggregate the question into a set of sub-questions, and the most important one is whether there are high potential crop processing throughput, but at the same time low projected economic feasibility of central grid connection or mini-grid development regions. So regions where we definitely see a potential for crop processing. However, we don't find it to be very much economically feasible according to the electrification model to bring the central grid there or to develop a mini-grid. Also here in the example, you can see a solar rice miller to get a better sense of what type of technologies and scale of technologies we are talking about. And to address these questions, we will use the electricity supply and crop processing dashboards and output data. So going back to the electricity supply dashboards, this time we select the standalone PV as the technology of interest and not anymore the mini-grid PV. And of course, we can see that the results change considerably. For instance, in this case, we can see a really large hotspot of standalone PV potential for electrification in the southwestern, western, and southwestern part of Zambia, as well as in the north of the country. The corresponding capacity requirements are displayed in the right-hand side dashboard. And moving to the crop processing potential, interestingly, we can see which potential crop throughput and electricity requirements for crop processing and cold storage emerge. Looking at the right-hand side dashboard, we can see that strong potential for electricity use for crop processing and cold storage is found in the really northern part of Zambia, as well as in the central part of it. As it can be seen comparing with the previous dashboard, there is not a strong, clear overlap of regions. So it's not a one-to-one relation. One needs to dig and, of course, identify what is the best trade-off between regions that benefit from solar PV electrification and regions that have significant electricity requirements, bearing in mind that it might be likely that regions with the very high demand, such as the central ones in central Zambia that you can see in one red circle, are also regions which are very close to the capital city and among the densest in population, so likely those with the highest chance of getting electricity central grid connection. So maybe not worth or of interest in the scope of the current example, despite their strong potential for crop processing and cold storage energy use. So maybe better focus on the northern part of the country. So again, these third use cases showed how the dashboards can be used to provide a first-order overview to identify processes and areas with the largest estimated demand for crop processing and standalone PV shares. And similarly to the previous example, it's, of course, just an exploratory analysis and to get a better sense where to target investments or where maybe to target a field visit to assess the boots on the ground, what's the current situation. It's better, or it's mandatory, I would say, to access final resolution data such as the settlement data and specifically explore in a GIS environment more in detail the within province heterogeneity to observe which communities, which districts are the most potential and promising one in this sense. So having understood why it might be really important in some instances to access the high resolution output data, which is underlying the provincial level summaries that are seen in the dashboards, we will now give a proof of concept of how to achieve this objective and browse the sub-provincial settlements to get a better sense of the local situation after a given province of interest has been identified. First of all, it's important to notice that when we are browsing onto one of the dashboards, any of them, if the user clicks onto one province on the map, we will see a pop-up appearing that not only shows the corresponding value, such as in this case you can see the electricity demand as we are in the corresponding dashboards, but also a web link with the download link to the high resolution data for the selected region will pop up. Again, why might be important to access that province settlement level data? To look at the distribution of demand across settlements in the region, for instance, and also to evaluate additional socioeconomic and demographic variables and visually assess settlement with the aid of satellite imagery, just to get a better sense of its location, of its geographical context. So once we click on the region in dashboard and we are prompted with this pop-up, if we click the web link, we will be brought to another web page, which is a repository of the results for each of the provinces and regions which are shown in the dashboards. And we will have the chance to download the raw disaggregated data for that specific province. So after we access this dashboard and we click the download button as shown in the red circle, the file will then download directly onto our computer. To open this type of data, which is stored in a JSON format, we need a GIS software. There are a large set of possibilities and alternatives to use Geospatial data processing tools on a computer. Here we will show the case of QGIS, which is the most popular open source and free alternative, as well as software that can run on all operating systems and platforms. So the software will allow us to browse through the data that we downloaded, so the region in question, and to visually observe the distribution of the settlements, and then perform some operations such as color them based conditional on the field of interest to get a sense of which settlements within the country are most promising for our goals, as well as adding maybe a background-based map such as satellite imagery. So to do this, the user will first open the QGIS empty project window and then drag inside our reference map, first of all. So we have the chance on the left menu to select among a set of so-called XYZ tiles that are background maps, which can be terrain maps, they can be satellite maps, straight maps, and so forth. Here we select the Google Satellite Hybrid, which is a combination of both political boundaries and elements and a satellite snapshot. On top of which we will then drag into the QGIS window the downloaded clusters file for the province of interest, which we will seek in our browser window and directly drag into the QGIS and wait for it to load. This is just an example of how the population clusters, which as a reminder are the unit of a reference of the MLED and onset model in the RE4AFAGri dashboards, how they look like, how they present, and how they are distributed with the context, useful context provided by the satellite imagery, which helps to better picture their geographical extent and location. As you can see, when you drag the clusters onto the QGIS, first of all, they are visualized with a homogeneous color, so they are not graduated by any criteria, just their extent and size is visible. Thereafter, a very important step that is recommended is the selection of the field of interest and filtering of the geopackage attributes. What does this mean? When we download the clusters for a specific province of interest, we get the whole set of information, which are then displayed also in the RE4AFAGri dashboards for each of the small settlement clusters, for all the variables, years, month, scenarios, and so forth. So as you can see, there are a large number of fields contained in the data, but perhaps we are just interested in visualizing and analyzing a bunch of them, as a limited selection of them. So it is really recommended to delete, first of all, as a first step, all the fields that we are currently not interested in analyzing, as these files are very large and heavy, and doing this selection step can really ease the process of browsing and analyzing the data and avoid waste of time in terms of lengthy processing times for given by the size of these files for fields that we will not end up using. So if we select in the processing toolbox, which is this menu on the right-hand side of QGIS, which contains all the GIS functions, the field removal tool, which can be found by typing remove field in the search bar, we will then be prompted with a window where, as an input layer, we will, of course, provide the clusters file that we just dragged into the QGIS. This should be the default option, a selection. But then, crucially, we will click on the three dots, as highlighted in the red box, to select which fields we would like to delete. And most likely, we would like to delete most of the fields, as we are only interested in a bunch of them. So we will first perform a select all in this window that pops up. So select everything, clicking the select all button. And then we will just mark out, select out those limited number of fields that instead we would like to analyze and visualize. So here I'm saving the non-farm SMEs total demand in 2030 for the ambitious development scenario, which is my field of interest. So by performing this operation and then clicking run, which will take a few seconds, we will come out with a much lighter and manageable file that only contains the clusters and this selected field of interest. Then we possibly might want to classify or encode the different clusters by color using this property that we just selected. Of course, we should apply this color ramp to the newly generated layer, which is the layers which only selected the fields of interest, as we did in the previous step. So we will see in the layer box on the bottom left of QGIS a newly appeared layer, and on this one, we will right-click and select Properties. Once we select Properties, we will be prompted with this new window where we should select the Symbology option, set of options, where we can define the colors and we can define criteria such as the color coding type, which, given this variable is numerical, I recommend to set to graded. And then also the name of the field or variable to plot. In this case, we just saved one from the old list. So we will select it and it's going to be likely the only one. And then we also have the option of selecting which color palette, which is an aesthetical choice, and the color coding rule, how colors are allocated to a range of values. And here for effective visualization, I generally recommend the natural breaks coding rule. So after all these criteria has been set, the user can click on OK and see that the QGIS window will now visualize the settlement clusters, but with colors that then are mirrored in the legend, which is shown in the layers panel. So demonstrating how the SMEs demand is distributed within different clusters within the regions that we are studying, and how different settlements have higher or lower estimated demand, and how much specifically is this demand. With regard to this last point, by clicking the button which is highlighted in the red circle above, so the mouse over with the eye of information, it's possible to select this mode of use of QGIS, where then clicking onto a cluster, so first clicking on this option which is circled in red in the menu bar, and then clicking on a cluster of interest. Here I clicked on this very large cluster that was displayed in yellow. It's possible to obtain the exact value, underlying value of the field in question. So I click on this very large cluster that then colors red, which used to be yellow colored in the previous image. And then this new panel opens up showing the number of estimated kilowatt hours of non-farm SMEs demand in 2030 in the ambitious development scenario in this specific settlement, which might be an interesting information from a planning point of view. We arrived to a conclusion of our online training sessions on the RE4AFAGRi dashboard from the LIPA-RE RE4AFAGRi project. We hope that this training was useful and inspiring for future utilizations of the dashboards, and we hope that you will be using them extensively. And of course, do not hesitate to reach out to us on the RE4AFAGRi website. You can also find a contact webpage where you can reach out to us for any query, request, or clarification question. Thank you very much.